In a series of experiments, a chemist prepares three different compounds containing only iodine and fluorine, and determine the mass of each element in the compound. Okay, so we have 1, 2, 3 compounds. A. Calculate the mass of chlorine per gram of iodine in each compound. Okay, so we do that, right? We want the mass of fluorine per gram of iodine, so we take grams of fluorine divided by grams of iodine, and we get how many grams of fluorine per 1 gram of iodine? Grams of fluorine per 1 gram of iodine. Grams of fluorine per 1 gram of iodine for the three compounds. All right. So, I really should have. Yeah, I'll have to back up. So, how do the numbers in Part A support atomic theory? The problem I'm having with this particular problem is it's not working, at least the way I see this is supposed to work. If I have a different problem, right, in another book, we had these compounds, this compound containing copper and chlorine in this case. And when you take that gram of copper per gram of chlorine ratio and divide one to the other, you get a whole number. This supports what's called the law of multiple proportions. It's a fact, right? Different compounds can be made out of the same elements by changing the proportion. So the question at the time was, well, why is this true? And Dalton's explanation is, it's because atoms come in whole numbers. So what you have with the difference between compound 1 and compound 2 in this case is that you have twice the amount of copper in compound 1 as compound 2, because copper atoms come as whole units. You get twice the number of copper atoms, therefore you get a new compound by combining with the copper. Combining the copper with the chlorine. Problem with these numbers is when you do the same thing here, we don't get whole numbers. So I don't know. I don't know what the author was showing with this. I don't know if it's my error mathematically. See if you can find it. I don't know. I went over it 6 times. I couldn't figure it out. So to me, it's supposed to support the law of multiple proportions, and I don't see it supporting it. How did Rutherford interpret the following observations made during his alpha particle scattering experiment? Okay, so his experiment was alpha particle is a helium nuclei, positively charged particle. And when he shot it through this thin slice of gold foil, it was one of the big shockers in chemistry. What he found is that 99.99% of the time you didn't hit anything, right? This big helium particle went right through the gold foil and had no deflection. So the idea was that if there was a positive part to the atom, this positively charged alpha particle should get deflected. The fact that it wasn't getting deflected meant that most of the atom was made up of nothing, and that it was very hard to find this spot where the positive particles were. But sometimes you get these huge deflections, right? So bam, straight back at the cannon. Boom, off in this other direction. It was almost like you hit something hugely massive. So what he deduced from this is that all the mass of the atom is located in the central area called the nucleus, and that's where the positive particle is. The fact that the positive particle of the alpha particle went right through the gold foil was because it was going through where the electrons were, and the electrons must have had no mass compared to the positive particle because you didn't knock the positive particle off its path. So most of the alpha particles were not appreciably deflected as they passed through the foil. Reason is because electrons aren't able, because of their size, to deflect the alpha particle off its path. B, few particles were deflected at very large angles. Well, that's because when you did find the nucleus, where all the mass of the atom was, this thing is huge compared to the alpha particles. What differences would you expect if you were dealing with beryllium foil as opposed to gold foil? Well, gold is a big atom. Gold has 97 protons, and since the most common isotope, gold 197, that means you've got a lot of mass in that particular nucleus. Unlike with beryllium, where you've got a much smaller nucleus, you're not going to get as big a deflection because it's going to be harder to find the beryllium nucleus as opposed to the gold nucleus. And when you do find it, I'm going to have to show this on my football analogy. So, like I was saying, right, my football analogy, right, what Rutherford basically figured out that is most of the atom is made up of nothing, and all the mass of the atom is located in this central area called the nucleus. So he does this by bombarding a beam of alpha particles through gold foil. An alpha particle is just a helium nuclei. So it's a positively charged particle that is going through the gold. And the idea was that if you encounter the positive particle of gold, you get a deflection. Now, gold is way more massive than helium, right? It has a mass of 197 AMUs as opposed to 4 AMUs. So here's your alpha particle. Here are the beta particles. These are the electrons, right? Little electrons, right? Way lighter than the huge football player. And then this is the image, the nucleus, right, with all the mass is in the center. So when you shot the alpha particles through the gold, most of them went through this area, right? The area where the protons aren't, which is most of the atom. I mean, I don't know, I always do the analogy of it's like putting a basketball in the middle of City Field. The basketball is the nucleus, then the rest of the City Field is the rest of the atom. So the rest of the atom is where the electrons are, and that's basically empty space. So the electrons are way less massive than the alpha particle. You say to yourself, oh, well, you know, the electrons are charged negative, right? They should have a tug on that big positive particle going through. Well, no. Right, the positive particle goes whipping through and is undeflected because it's so much more massive. An electron is like 1/2000th the mass of a proton. So if I'm looking at a close-up instant replay, here are my little electrons. Here comes the path of the alpha particle, and when it whips through, there is no deflection, right? These little electrons can't deflect that huge alpha particle off its path. So whipping through the gold foil, right, hitting nothing. Whipping through the gold foil, hitting nothing. It's only when the alpha particle lines up so it's going to collide with the nucleus that you get a deflection. And because the nucleus is so much more massive than the alpha particle, you can get huge deflections, right? It's almost like you've hit this immovable object, hitting this huge immovable object. So this is it. This is how they determined that all the mass of the atom was located in the huge positively charged nucleus. Answer the following questions without referring to table 2.1. What are the main subatomic particles that make up the atom? Okay, so at this point in the course, we've already talked about that there are protons, neutrons, and electrons. And it's these, well, subatomic particles, particles that are smaller than an atom that make up the atom. B, what is the relative charge in multiples of electronic charge of each of the particles? A proton has a positive charge, a neutron has a neutral charge, and an electron has a negative charge. Right? So these positive and negative charges are equal and opposite in magnitude. C, which of the particles is most massive? Well, the proton is 2,000 times more massive than the electron, and a neutron is about the same mass as a proton. So massive, massive, and then extremely less massive. Electron's a weird particle. You know, 1/2000th the mass of the proton and the neutron, but equal and opposite in charge. So a very small but highly charged particle. D, which is the least massive? Oh, there it is. Okay. As we said, 2,000 times less massive than either the proton or the neutron. Determine whether each of the following statements is true or false. If false, correct the statement to make it true. The nucleus has the most mass and comprises most of the volume of the atom. Well, the first part's true. The nucleus is where all the mass is. The electrons, because they're 1/2000th the mass of the nucleus, do not really contribute any mass. It's all about the protons and the neutrons, but not the volume. All right, so protons and neutrons are, make up very little of the space that an atom occupies. Most of the space is most of an atom is empty space. Every atom of a given element has the same number of protons. Yes, that's what defines a particular atom, a particular type of atom. There's only one atom in the universe that has 6 protons. That's carbon. There's only one atom in the universe that has 2 protons. That's helium, and so on. What is the number of electrons in an atom equals the number of neutrons in an atom? No. If you have a neutral atom, the number of electrons is equal to the number of protons. And D, the protons in the nucleus of the helium atom are held together by a force called a strong nuclear force. Right. If you've thought about a nucleus, right, this is where the positives are located. If you put a positive charge with a positive charge, they want to repel. So if we're looking at the nucleus of an atom, right, talking about the strong force here, protons next to a proton, they want to repel. They want to get away from each other according to electromagnetic force, electrostatic repulsion. So what's holding it together? This thing called the strong force. The strong force is the strongest of the 4 forces of nature. It's just that it only acts over a very short distance. So once you jam the protons close enough together, this hooking action takes over and holds them together. And what holds them together is the strong force. Neutrons also will exhibit strong force. So neutrons act in a nucleus as a kind of a glue, gives you more strong force in countering that proton-proton repulsion. So the strong force, that's what holds the nucleus together. That's it. There's only 4 forces in the universe. Electrostatic attraction, repulsion, gravity, right? Anything that has mass has attraction for another mass. The strong force holds the nucleus together, and the weak force is a force involved with nuclear decay. It's very weak. Define atomic number and mass number. Okay, atomic number is the number of protons in the nucleus. The mass number is the number of protons plus the number of neutrons in the nucleus. Which of these can vary without changing the identity of the element? And the answer is the mass number, right? By changing the number of neutrons, right? You're not changing the identity of the element. What you're changing is how massive it is. So when you have the same type of atom with different mass numbers, you call them isotopes. So when you stick your hand into a bunch of carbon atoms, most of them come out as the isotope carbon-12, meaning you've got 6 protons in the nucleus and 6 neutrons, so a mass number of 12. Whereas carbon-13 has an extra neutron. All right, so same atom, different mass numbers, we refer to them as isotopes. So yeah, not all carbons are the same. Some of them are carbon-13, some of them are carbon-12, some of them are carbon-14.